Technology.
Welcome back to Technology, everyone. We Precious here again. You know, in the past, Kyle and I, we used to talk about what is more interesting, space or the ocean. We would often disagree, and I have always been a fan of space, and I think it's so mysterious, but I understand why the ocean is so intriguing. I mean, there's so much to explore, but there's so much going on right now in terms of space discovery. We've got the James Webb Telescope, we have the recent Artemis mission. There's just so much happening, and so I'm really glad and really fortunate to have our next guest, Jesse Rogerson, who's joining us. He's assistant professor at the University at York University in Toronto. And Jesse, welcome to Nobody. Really happy to have you here, and thanks for making time.
Yeah, I'm happy to be here. I will always show up for an argument over whether space or oceans are cooler. So
I'm looking forward to hearing all your insights on that. I was before this, I was checking out your Instagram page, and you know you're on the media and talking about space and such, and I saw a cute little photo of your is it your daughter, I guess, that was kind of looking at the TV and just fascinated that dad is on TV. Is that still kind of an interesting experience just to be on TV, or like what was
Yeah, well, when I do the media stuff, so it can be anything from I've done like blog, like I've been quoted in like articles, or been on the radio, or been on TV itself once in a while. I really savor those opportunities because it's a chance to connect with a wider audience. And engage with science, and just hey, remember, space is there and there's cool things happening. But then, as you pointed out, that it's after Charlie comes into the world, our daughter, my wife took that photo of me on TV and her like looking up. I was like, holy crap, this is a whole other dimension now, because it's no longer just a wider audience. I also, when I saw that, I was like, oh no, I'm also speaking directly to her too, and it sort of renews the interest I have in engaging people with science and how important science is, but that it's also such a personal thing. It's such that photo is, it definitely made me reorient how I communicate or why I'm communicating science.
It was really, really neat to see that. So you're a fairly young dad. How old is Charlie?
I think she's 16 months now in a couple of days. Okay. 16 months, I think, is right. Yeah. So she's full on, she's like walking and she's blabbing around like crazy, and she's, for parents, as you probably know, like it changes so fast. So like you feel like you got the hang of it, and then like the next week she's like a totally different person, which is great and challenging. So it's been quite a ride, that's for sure.
How does she keep busy? Like, do you allow things like screen time at this age, or is that something
good? Yeah. So I don't know what screen time means, because does that mean that she's the one actually holding the phone?
Well, I think it's that, or
does it mean like the TV's on?
I think either of those screens. The
TV is on all the time. Okay. So yeah, maybe we have it on too much. I don't know. But she definitely enjoys her Disney movies. Okay. Even though she's only 16 months, she has like favorites already. Okay. That she'll want to watch over and over again, and we try not to do it all the time, but it is on. It's frequently. We haven't really. I've read stories and studies about this, and there's ideas that you should limit it as much as possible, and maybe we should be doing that. What do you do? What's your rule at home?
We did have a bit of screen time. I'm trying to think. At 16 months, I think there was a little bit of Cocoa Melon and a little bit of the Wiggles, maybe. But it would be very limited, like maybe 20 minutes, and then it kind of started to expand, and now she's 4.5 and turning 5 soon, and she gets about an hour. And I mean, and then special occasions she'll get to watch her movies and such, and so that's kind of how we do it. But
I find that Charlie isn't really after, even if you put it on for her, after about 20 minutes she's bored and wants to go play and do something else, right? So you can't sit her down and have her just sit there and watch the TV. Yeah. She's not going to do that. She'll do it for like 10 minutes, and then she's off like grabbing blocks. She's a big fan of blocks, and we have these little plastic balls that she loves. And she's always she runs around the kitchen island just holding the two, and she's just running around and she'll throw them and stuff. And she's very, very, very much enjoys looking out the window when she hears trucks and loud cars.
Okay.
She's always like pointing at the window, like, so the screen, like if she was sitting at the screen watching the TV for an hour and a half, then I would be worried. Yeah, but she doesn't seem to be too interested.
Yeah. Do you find yourself as a new dad? Like, I still feel like I'm doing this, but like I reflect on my own childhood as I'm parenting. Does that come into play for you at all?
It definitely does. So we have one. My parents had four,
okay.
And I can't believe what blows my mind is I can't believe how much one-on-one time I got as a child in a house of four children. Like I felt seen all the time, and I didn't realize that at the time. But now having the one child, I'm like, holy crap, my parents were able to actually give us attention in that whatever chaos that must have been. They did it really well, and we're thinking about what happens if you have another one and how do you divide your time between two, and because we give Charlie all of our attention, so how do you that's sort of where we're thinking right now, and that's definitely a reflection I've had is time with the child.
That's amazing that your parents, 4 kids, and the amount of presence that you're saying that they showed, because I don't know what sort of era that, like what decade that was, but I feel like back in the day, like it wasn't it wasn't known to be a major priority to be present with your kids. Like now there's so much more research and so much encouragement to have and what that quality time means and how that affects future development, and we know these things a lot more. But for them to to have that sense to like, hey, we got to make sure that each kid has time. So,
and I can that presence, you learn so much from them. Like in my job, like I find myself doing like organizational things that my dad taught me how to do when I was in like high school. And I'm like, this is why I'm doing it, because my dad told me to do it this way. And now I'm like still doing it that way. And for better or for worse, I'm sure there's other traits I have that maybe I wish I didn't have that come from my parents. But the presence of them being there, like I learned a lot from them. And I want to do the same, right? I want to show Charlie everything and teach her as many things as I can, right?
Yeah. What's the challenge that you're experiencing? I mean, I imagine your day job is probably incredibly busy, and having a young kid. I mean, every parent, probably parents go through this. But what does the challenge look like for you? And just having to be present and trying to maintain a certain schedule and what does that look like for you right now?
Presence is difficult. So as a professor, I teach a variety of courses, and they're not all like, it's not a 9-to-5 job. Like some of my courses are like, I teach some days till like 9 p.m. Next semester I'll be teaching frequently till 7 p.m. And so like I'm already missing things like bedtime, and bedtime is at this age really great because it's so precious. You get to read books. I read space books,
of course.
And she points out pictures, and she blabbers on, and then I get to put her down. It's really intimate and nice, right? And I'm gonna miss that, a little bit of it next semester. I'll get some days, but not as many. And then, but even then, like even if I don't get that, I'm still worried about how much time I have during the day. So the job is busy, and trying to balance like actually giving quality time to a child is difficult. I'm so lucky to have such an amazing wife. Alex, she works so hard, and she's so strong, and she is always thinking about what's the next steps for Charlie. And I try my best, but she's way, way better than me at it. And so there's so much good connection happening parentally. But I'm always trying to be as good as my wife.
Yeah. I don't know if you are experiencing this, but something I experienced probably over the age of 3 was my daughter didn't want anything to do with me. That was really, really
no
hard.
way.
Yeah, that was really hard because I pride myself on being present and being there as much as possible. She wanted anything to do with me. She would just always want mom to put her to bed. I'm like, what changed? Like, what did I do? And it was very hard. But it was good to talk to other dads, because there were other dads that experienced the same thing. And I don't know if it's especially if father-daughter relationships. I don't know. I think there's a certain specialness to that one. And so, like, I don't know. I find like I'm trying extra hard to kind of relate and be that kind of girl dad. And so to have her kind of push me away was really hard. So I don't know if you're experiencing that, but maybe that might come. So I just kind of heads up on that one a little bit.
So this is interesting. So did it come back? Is my first question.
She's good now. She loves Dad, and it's a lot of like I want to be with Dad, which is amazing. And I also found out that from some research in the States that sometimes why that happens is because they feel so secure in the relationship with their dad that they don't feel like they can push them away without knowing that Dad is going to come back. Like they don't have that insecurity issue. So when I read that, I was like, okay, that makes me feel better. It still hurts, but makes me feel better. But
so this is one of the research that I was reading is I really want, given the culture that we have in Canada, around the world, I want her to be strong and confident to be able to say no and express her feelings without fear of reprimand, right? So, and especially towards a man, to be able to say no and then have that be valued, right? So it's almost like if she does do that to me and pushes me away, I'm gonna be like, yes, good job, but then I'll be like, oh no, like wait, that means I don't get it, but maybe it's a sign of strength of strong-headedness, which is really good, ability to express the word no and have that be valued at home. So they recognize that. So I'm constantly sort of worried about that, where I want her to feel strong. Right. That's what I want. Right.
Yeah. That's it. That never ran through my mind. It hurt right to the heart. So I never really thought about like, oh yeah, she's exercising.
It's still gonna hurt
the
me.
Power of her no. But I think that's an interesting way of thinking about it. The space.
You ever see that show, Kids Ruin Everything?
No. Oh yeah.
There's it's a funny little sitcom, and there was a great moment in that show that was just exactly what you just said. It was like, I prefer Mom to put me to bed, and it's like, ugh.
What did I do wrong? The space books that you read here. Any favorite kids space book that you recommend for viewers?
Let's see. What do we read? So we have the Cat in the Hat one. There's No Place Like Space. Okay. So what's great? When she was born, we're newbies, parents. We didn't know what we were doing, and we actually found that when she was like 3-4 months old, she couldn't lift her head, whatever it was, we would read that book and she would kind of like just watch it. And maybe it would have happened with any book, but I wanted to read the space books. And I got to the point where I memorized the book because I read it. Like I could read it without looking at it, and I just show her the pictures. So we still read that one a lot, although I've forgotten all the words now. There's what's the other one? Oh, I forget. Oh, so one that we read frequently is not a space book, is a Canada book. Okay. And so that's
more geographical.
It's Good Night Canada, and that's a geographical one. So I want her to learn. Yeah. There was another space book. I forget. I'll think about it. Okay. There's another one that we do read. Oh yeah, we have a few. There's like a solar system book. I don't remember who wrote it, but it's got really abstract pictures of the planets and the sky. So it's got kind of like almost like a Picasso-y feel, kind of like geometrically kind of messed up. And it has like a comet going through the sky, and the book is really nicely done where it speaks to the kids saying things like, what do you see in the sky? And there's all this stuff in the sky, and she can point at things. And so there's that one. And then and then there was this, I think my aunt got it for me. It is Astrophysics for Babies. And I read that to her once in a while, and it's like a crash course in astronomy on how stars make elements and how the elements are part of the human, and it's like stuff that I teach in my classes at York in like 5 pages with only a sentence per page is a really fun one. But it got lots of nice colors in it, so I think it engages with her really nicely.
Okay, I was gonna say, is that the closer? Is that the book you do at the end, so she just goes to bed? Like,
it's time to learn astrophysics. Time for sleeping. Yes, like all my students in my lectures. Yes.
Your story in terms of how you kind of got into astronomy. Like, is that sort of an early age, or where did that fascination come from?
Yeah, I came to it late. I would say, like, looking back on it, I remember I was in like Boy Scouts, I think, or Beavers. I guess that's the same thing, like Scouts Canada, when I was really young. And I remember there was one night where someone brought a telescope and we looked at Mars. That's like one of the only memories I have from Scouts. But honestly, it wasn't like a career driver. I thought, oh, space is cool. I remember in high school, I really liked physics class. Physics was so grounding to me because there were very few scientific principles, and you could use them to explain so many scenarios.
Yeah.
Like you could there's an equation that you could get, and if I hold a ball 1 meter above the surface of the Earth, I can tell you exactly how fast it will be going when it hits the ground. And like that was like, I don't know, it felt powerful to me.
That you could get with physics, maybe.
I really liked it. Yeah, the certainty. Yeah. I really liked physics. I really liked it, and I also really liked computer science, which at the time, so this was in the late 90s. The computer science class, we were learning Java, and even before that, we were learning Turing. I don't know if you remember that language.
Turing, no.
Great language. It was really fun. So I got really into the certainty and the problem solving of computer science. In high school, they'd be like, okay, write a program that acts like a calculator, and then you're sitting down, you write code, you test it, you play with it, and it's problem solving. And physics is the same thing. Physics is just, here's a problem, use your tools you've learned, and solve the problem. So those were like my subjects. Astronomy was sort of folded into physics in high school in almost an afterthought, kind of like a last unit that sometimes didn't get covered. Yeah. In grade 12, they did do special relativity, though, which was really cool. Yeah. But all of this, I never saw it as a career. It was just, space is cool. And I went to university as a computer science major. I went to McMaster because I thought that was, maybe it'd make me money. I don't know. Sure. I get a job. Computers are around, right? I don't know. So I went there. And when I was in first year university at McMaster, I hated it. I hated computer science. It did not like it. I don't know what it was. I loved coding. But whatever the courses were that I was taking, I didn't I had a different view of what computer science was. Yeah. It was very theoretical. It was very mathematical. And so I kind of didn't like it. And I couldn't see myself continuing it, which was kind of scary.
Because when did you realize that? Like in the middle of your degree, or
actually in the first 2 months. Okay. So, which is good. Yeah. It was an easier pivot. And then so but when the first semester ended, I was like, I need, I'm 18 years old. I need to figure this out. I don't want to do computer science. And I had taken as an elective at Mac astronomy, introductory to astronomy, because you need to take electives. And I was like, I like space. That's cool.
Yeah.
So second semester starts, I'm taking astronomy, and I'm like, oh my gosh, this is all the stuff from physics that I liked, but only astronomy. Right. And you're learning about gravity, and you're learning about motion, and you get to learn about the planets. And it was being taught by this professor, Ralph Pudritz, at Mac, who's a fantastic lecturer, very engaging, very good with his students. And I fell in love with it. But I was still in this world of I don't know what I'm going to be doing. And so I started going to all the open houses of the faculty of science, because I knew I was a science brain. So I went to the geology department, and I like geology. That's cool. Rocks are cool. And I went to environmental science, which is slightly different. And I went to, I didn't go to chemistry because I did not like chemistry. No, and then I went to the physics open house, and there was this, the guy there, I think it was Ken Sills, a great professor at York. And he was like, oh yeah, physics is great. You can learn about space. You can be an astronomer. You can do this. It's going to be fun. It's a lot of physics and a lot of math. And I was like, okay, I like physics. I'm not great at math. And then I just dove in. and I dove in, and I was like, well, I'll give it a shot. And in my first year, I had to take a couple of astronomy classes as part of my major. Sure. So this is second year now. And that's where it really became clear. It's holy crap, I can spend the next 3 years just learning about space. And so I was all in at that point. And so as you can see, I didn't come to astronomy until I was maybe 18, 19 years old. I never owned a telescope. I never went to space camp. I never did anything like that. But it was trying to figure out I really fell back on what it was obvious interests, which was physics. And the cool thing is once I got to grad school, I realized how much programming is required in astrophysics. Oh. So I had all these fundamental skills. I didn't have a lot of programming chops, but I understood what programming was, and pseudo languages, and and problem solving. So by the time I got to grad school, I had a good foundation of programming to build on.
Was grad?
So that's At the end of my 4 years, I was like, well, I'm not done learning about this. I really, really like learning about space. In fact, now I want to start doing the research that I'm reading about in these textbooks. And so I went to grad school, and here I am.
Well, that was my next question. Is sometimes like if people just fall into grad school, is it just a bit of an extension of your bachelor's? Like, was that grad school was purposeful for you? Would you say?
Yes, it was purposeful. I wasn't done learning.
Okay.
I knew I wasn't done learning about space, and the only way to continue was grad school, because otherwise you have to go and get a job somewhere, right? And then you're only learning about it on the side, which you can do, but I wanted it to be my whole life at that time. So grad school was the way, and I found a really great professor at York, Dr. Patrick Hall. He's a quasar expert, and he's such a fantastic educator and an even better researcher. And he had some really cool projects, and after speaking to him, I was like, yeah, like I want to do what you're doing. So it was purposeful. It was also, I didn't know what to do next. To be totally honest, I think a lot of grad students do that, where you get to the end of 4 years and it's hard to know where to go next. And I knew I wasn't done learning about space. I didn't know what kind of jobs I could get with a 4-year physics degree. So a grad school seemed like a great option, and it was like, I can see what I can do with. The decision was, okay, I can spend 2 years doing a master's, and that can help me decide what an astrophysics career looks like, which it did very, very well. And I can get into that. That's the next step of the story, right? So,
what I was going to say is like, what does an astrophysics career look like? Like, is it mostly on the research side, or what are those different options?
Oh man, it depends on who you talk to. Okay. But they're all over the place. And I would say an astrophysics education is a very versatile education.
Interesting.
So I did my master's, and you're learning hardcore theoretical physics, hardcore observational physics, and astronomy. All astrophysics is just physics in space, right? And you learn all these you learn how to problem solve with your brain. You know how to look at a problem and dissect it to what you need to do. You learn a lot of coding. You learn how to use big data sets. You learn how to look at data and uncover different relationships. So you could be given data sets and be like, okay, we have this data set and we're trying to answer this question. And so you start playing with the data and you start, if I graph this and this, or if I change this variable to this variable through this calculation, and then, you're working through this like problem solving to massage your data to answer a question. And those are like very versatile and useful abilities. If you look at anybody in the data science world, which is like a whole new that's a whole new field now. For sure. In the last 20 years, it's exploded. And I have good friends from grad school who finished their astrophysics grad work and went straight to data science and are doing great things with their work. So that's like one direction you can go. You can become a hardcore astrophysicist and be a researcher. So that's where you're trying to get hired at a university. You're going to be a researching professor. You're going to have grad students. You're going to write telescope proposals, or any kind of or grant proposals, and build a research lab. And you can do that too. And then the route that I went, which is much more in keeping with myself, is an education and public outreach route. There's only so much room in the world for researchers. There's plenty of any other cool things to do, and I finished my master's, and I wasn't done learning. I knew I wasn't an expert yet, so I started my PhD, but I also knew that I wasn't going to be a researching professor at that time. I like research. I want to learn, but I was having so much fun educating people. I wanted to be in classrooms. I wanted to be on the sidewalk. I wanted to be in museums. I wanted to tell people. I didn't want to just learn it. I wanted to tell people about the cool stuff that I've learned. So I started building a career that way. And as a PhD student, I got a part-time job at the Ontario Science Centre, which was absolutely formative. I volunteered at the York University Astrophysical Observatory, which is now the Alan I. Carswell Observatory, under Paul Delaney. Absolutely formative. Very, they do a lot of public outreach there. And then when I finished my PhD, I was like, I'm going to museums. I'm going to go work in museums. I'm going to educate people. Yeah. And so I freshly minted astrophysicist with a PhD, and I went and I worked at Telespark in Calgary. And then I ended up at the Ottawa Canada Aviation and Space Museum as the science advisor. And that was a fantastic experience. Amazing people at that museum. And it was, all those jobs were all about taking the world of science and figuring out how to engage people with it and how it fits into their lives and why they should care about it. And it was really, really fun. You get to meet people. You get hands-on with the engagement. Yeah. And that was really, really fun. So that's what I built my career into.
Yeah. I feel like, I think that the route that you took, like, is maybe a bit unique, because I imagine that many folks who go into their PhD, like, the focus thereafter is probably like, I'm going to be a researching professor or go into research or that sort of thing. And you find more, like, at least the time when I was more in academia, you find that a lot of professors don't want to do the teaching. They want to just focus on the research, right? So I imagine that there was probably a really good, like, space for you to take this on, right? Like, maybe not as many people would want to do the education and outreach part of the work that you were doing.
That's a good question. You know, the industry is slowly evolving to make more space for it. The classic university department is researching professors who are teaching. They have like most of their job is research and some of their job is teaching. And you want that because you want your undergrads to learn from the people who are actually doing it. But then, you know, their focus is research and they're really good at what they do, but you also want to have some influence from professors whose work is to be a good educator. Not that a researching professor is necessarily a bad educator. It's just not. It's like now what I've done is I've left the museum world. I'm back at a university, but I'm in a teaching stream, and my entire job is to how best to deliver this content to undergraduates learning about space. And so I can really steep myself in really good pedagogy. Ways of playing with the classroom to get students to work hands-on as much as I can. So the university space, I think, is especially at York is nicely evolving towards this, to have more of these teaching stream professors, and you have a good balance of researching stream and teaching stream, and you get a good mix of skills that the undergraduates learn from. So I think that's really, really good. I would say that from my experience doing my PhD and then moving into the museum world, the jobs were kind of not there. Like, museums weren't looking for what I was offering. Because museums have their own specialities. They have really fantastic interpreters, and curators are incredibly good at what they do. So the museum world also was kind of like, is starting to sort of, how do we take someone with a PhD in science and put them in these roles in the museum world? This is my ultimate goal. I've always told this to people. I want to blend that, like, the education, science, university world with, like, the public education, public outreach, engagement, museum world. The more those sort of two blend together and overlap with each other, the better both audiences learn the material. So I think there's a nice trend over the last 15 years or so of museums coming a little bit to the academic side, and academia coming a little to the public outreach side. Yeah,
there seems to always be this challenge in academia of knowledge transfer, right? So it sounds like this is, at least in the world that you're living in, that this is starting to happen, you know, in a better way, I suppose.
Oh, definitely. I like, York is really great. They have York, both researching stream and teaching stream. Professors at York we have some incredible educators there that do some wondrous. I'm learning every day how to be a better professor from the people at York. They're so good.
I was reading a little bit of it in your bio on your academic page about how you spent some time in different parts of the world. Now, I don't know if it was looking through some of these major telescopes, but like in
Yeah.
Hawaii and
Yeah.
California and Chile and Arizona. But like, are we talking about those massive telescopes that people? Yeah, is that what we're talking about?
Yeah. That was one of the things when I left my undergrad.
Yeah.
I had an undergraduate thesis supervisor, and I asked her, I'm like, I want to look through telescopes. That's what I want to do, because I didn't do that as an undergrad. And she directed me towards York, actually, and she helped me get into York. And I ended up with Pat Hall, and Pat Hall is an observational astronomer using optical telescopes. So if the light that comes from the sky, the light that the human eye can sense is called optical light. And there's this entire electromagnetic spectrum from the X-ray off to the radio and everything in between. So you have X-ray, gamma ray, or gamma ray, X-ray, and then you have UV light, and you have optical light, and you have infrared light and radio light. And Pat is an optical astronomer using optical telescopes, the classic telescope, that you think you put your eye to and you look at the sky. So I stepped in sync with him, and we started. And one of the first things he got me to do as a PhD student was start writing telescope proposals. And
I didn't even know
that
got me off to telescope proposals. Yeah, I don't even know what that means.
Oh man, it's like you have to tell. Okay, what you do, it's awesome, and it's a ton of work. There's some telescope out there. For example, we use the Gemini telescope a lot. Which is a twin telescope, one in Hawaii on Mauna Kea, and one in Chile.
Okay.
And they're identical telescopes, and we wanted to use them to monitor quasars, which we can get into in a bit. But what you got to do is you got to write this proposal to them, and what you say, okay, here are the 10 objects I want to look at. So I already know what they are. I already know all this about them. I want to look at them with your telescope, with this specific instrument, because there's multiple instruments that you can put on the back of the telescope. Okay. I want to look at each one for this amount of time. This one needs 30 minutes of observing. This one needs an hour and a half of observing, etc. And after I do all of that, here's what I'm expecting to learn. And you write page after page of all the science you're expecting to learn from the observations you're going to get from their telescope and the papers you're going to write from that observation. And then you submit it, and they get submissions from all the other astronomers, and then they have a team of people who look at all the proposals and decide who gets time on the telescope. It was like the first time, it was probably my first real training on deadlines, because the telescope is like, this is the deadline, and that's the deadline you need to submit. It's a lot of work. It forces you to learn your science, because you need to communicate what you want to do. And luckily we got a good amount of time, and we were able to observe. In the astronomy world, in the professional world, we have two kinds of observing. We have queue-based observing, which is where you write your proposal, you get accepted, and then you send them all the targets, and they do the observations, and then they send the data back to you, and you don't go anywhere.
Okay.
And then they have classic observing, whereas you go to the telescope, you stay up all night, you move it around the sky.
Which sounds like a whole lot more fun, by the way.
It's way more fun. And I got the opportunity. Where did I go? So I went to Kitt Peak a few times. That's in Arizona, just outside Tucson. Okay. Incredible skies, very dark skies, very dry skies, and is like sort of the center of optical astronomy for the United States. So on the top of this mountain in the middle of the desert, there's like 15 telescopes or something like that. I went to California, just outside of San Diego, the Palomar Observatory. That has a 5-meter telescope. It's 5 meter. The mirror on the back of the telescope is 5 meters wide. Okay. It was once the largest telescope on the planet.
Okay.
And then where else did I go? I think that's it. I think those are the only two places that I myself went to observe.
Okay.
Yes, and then the ones in Hawaii and Chile were queue-based, so I didn't actually get to go, unfortunately, to those places.
Okay. And what is it like when you look through these telescopes?
Well, you don't actually get to put your eye to them because they have cameras on the back, and so what you see so you're sitting in, I have a bunch of great pictures I could show you. You're sitting like at a desk in what they call a warm room, and that warm room is separate from where the telescope is, and you have there's any windows that all the light is stopped so that no light can get into where the telescope is from your room. And you're sitting, there's like probably 5 or 6 monitors around you. One manages the telescope, and one manages the instrument, and one manages this and the dome, and there's a bunch of stuff. And you're just coding and you're typing and you're moving it around, and then you hit go and you just sit back and you let it do the observation, which means the telescope is pointed at the target you want to collect data on, and then you open the aperture so that light is allowed to hit the CCD, which collects the light, and say you need it to be open for 10 minutes as it constantly collects light from the same object. And then it closes, and then it'll read out onto your screen, and you see it like, it's almost sometimes like a line by line, the readout, and you get this sort of like black and white image of this target, and it looks like nothing, but it's amazing. You're getting this light that's been traveling through the universe that's fallen into your bucket of you've collected it with your light bucket, your telescope, and you're like, that's my light now. Like I collected it. It's on my CCD. It's wild. It's a wild experience. But one of the things I really liked about it was not the collecting the observations, but then hitting the go button, and then I could step outside for a second, and these places are in such remote locations that the sky is like unlike any sky you would ever see in even a small, even like obviously Toronto and the GTA is a light bubble, but even like in smaller little areas around Toronto, the sky is not even close to what you would get in these like middle of the Arizona desert or middle of the mountains in California, and that was a really great experience.
We, my wife and I have been a couple of times to Jasper because we're here in Edmonton. Went to the Dark Sky Preserve, and it's amazing. Like it's amazing what you see. But some of these folks who have these massive telescopes themselves, and they're like, "Yeah, you want to see this one star or whatever it is?" And we're like, "Okay," and we have this expectation of what that looks like. And it's just a dot of light, and we're like, "Yay!" And so it's kind of underwhelming. Like it's it's cool. Like I think the way you described it was really neat. Like it's this light bucket, and this light that's traveling from so far, and I really appreciate that narration. But that's not what was going through my head when I would look at these things for the first time. These massive telescopes. So
what's crazy is stars are like completely unremarkable through a telescope, right? You look at them and you're like, it just looks like what it looks like when I look at it with my eyes. And that's got a really cool when the first telescope started being used in like, this was like Galileo times, like Galileo was one of the first using a telescope, and they pointed them at stars and they pointed them at planets, and they realized how different they were, because when you point a telescope at a star, it still just looks like a little tiny point of light, but when you point it at a planet, you see the planet. You don't just see a point of, like, if you and I went out and I said, "Hey, there's Mars," it would look like a red star, a pretty bright red star. But then if we pointed a telescope at it, you would see and you would even maybe see a little bit of the like different colors of the surface. Totally different experience. When you did it with in Jasper there, were you able to look at a planet?
No, they were just pointed. They were just pointed at certain stars or whatever. So.
Oh man, when I was in my 4th year at McMaster, we had to do this observing project with Ralph it wasn't with Ralph Pudritz. Sorry, I forget the professor. We had to do this observing project, and myself and a couple of undergrads and one grad student, Rob Cockcroft, we borrowed the university's telescope, and we went out to a dark sky preserve just outside of Hamilton, and we set it up, and it was the first time I had looked through a telescope since I was like maybe 7 or 8 years old, and we pointed it at Saturn. And it just blew my mind because I could see it. I looked through the telescope and I could see there's the planet. I could see the rings. I could even see one of the moons, Titan, the largest moon. And it was a moment where I realized like how you can almost like reach out and touch it. Like that point of light you see, it's a whole other world. And it doesn't take much to see it. You don't even need a strong telescope to see the rings of Saturn. So next time you're at you see a telescope, someone got a telescope out, say, hey, are there any planets up right now?
Yeah.
And get them to point it at it.
Yeah, absolutely. Have you ever seen these YouTube videos where people take their real strong digital lenses and they shoot it at the sky and they're like, wait for it, and then all of a sudden Saturn just appears, and it just looks so magical. Like, it's incredible.
Oh man, it's a wonderful experience seeing a planet for the first time, especially Saturn or Jupiter or Mars. They're very impactful images. Yeah, I would say.
Yeah, very cool. We have this major telescope up right now in space that was launched, the James Webb Telescope.
Yep.
Like, what? First of all, I want to hear your thoughts. I want to know about why it's such an incredible scope. But just for them to get it out there, right? Like, wasn't that quite the ordeal? Like, didn't it have to unfold itself or something like that?
Yeah, that was a complicated mission to get off the ground.
How long were they planning that?
To say the least.
Like the James Webb.
Oh man, decades. Oh, okay. Like they were probably planning that mission from. I mean, you can trace it back pretty far, like the early 2000s. It was really, really humming along as a project. When I started grad school, which is like 2000, I think it was 2007. They were like, yeah, it's right around the corner. JWST is going to be launching. And I was like, cool. It took until 2021 for it to get off the ground. It launched on Christmas Day last year. And so what you had to do for JWST, the James Webb Space Telescope, is it's a 6-meter telescope. So what that means is that the primary mirror that the light is bouncing off of, the first thing that the light hits, is 6 meters wide. Now, a single 6-meter wide mirror is impossible to launch into space. And the reason you put it in space, if you're wondering, is because we, on the surface of this Earth, are below a very thick fluid that we call our atmosphere, which is just... It's like, you know what it's like? This is a great analogy. Imagine you're in a swimming pool, and you swim to the bottom of the pool, and then you look up to the surface and you try to see what's going on above the surface, like people walking around the pool or something, and it's all like jumbly and weird. You can't look through it,
like
right?
A huge filter, essentially. This atmosphere.
Exactly. Yeah. That's what's happening. You go outside, you're looking through 100 kilometers of gas, of atmosphere. And we've found great ways to manage that, but a really great way to get around it is to put your telescope in space. But you can't put a 6-meter single mirror in a rocket ship. It doesn't work. So what they did is they segmented it into these little pieces, and then they folded it up into what would fit in like the nose cone of a rocket.
Wow.
And so the engineering required to develop a telescope that would then go into space and then deploy itself perfectly with no human intervention possible took, I would say, 15 years of development and testing to get it right. And the most important thing is that if it went wrong, there was nothing they could do about it. Yeah. So they took their time. They engineered it very well. It unfurled perfectly, and it's operating, and it's taking data, and it's the next generation of space telescope.
So 6 meters. How does that compare to like the mirror that's on Hubble?
Hubble's 2-ish meters. Oh shoot, 2 meters. 2-ish meters.
And Hubble's still operational, though?
Hubble's still operational. What they were doing with Hubble, because Hubble's at like a 500 or 600 kilometer orbit. Okay. It's not that far up. Like, what's a 500 kilometer drive? Is that like Edmonton to Calgary?
I don't know. More than that. Yeah.
Yeah. Right. That's not that far, right? Yeah. That's where Hubble is. Yeah. It's just up, right? But they put JWST at 1.5 million kilometers away. So Hubble is close, and could be serviced. You could go and fix it, and they did that 4 or 5 times. They flew up with the shuttle and they fixed Hubble a bunch of times, and so it's been able to maintain science over 25 years, 30 years, and so it's still operational, but it will not be serviced again. Once it breaks, it's done. Whereas JWST was designed to be launched to where it is, and no one's ever going to go and fix it. So it needed to be perfect. But it's great that they're both operating at the same time, because Hubble is an optical telescope and UV telescope, whereas JWST is an infrared telescope, which are two different portions of the electromagnetic spectrum. And so launching JWST, it doesn't replace Hubble. It like adds on to Hubble. And as soon as we lose Hubble, then we lose the optical side of the spectrum up there. So it's great to have them both operating at the same time, giving us great coverage of the electromagnetic spectrum.
So does JWST, it doesn't have any optical component to it then?
No, it's only an infrared telescope. Yeah, so the light that it collects is light that is redder than red light. So if you look at the rainbow that we see with our eyes, you have like stuff on the bluish end of stuff, and then the reddish end. And JWST looks at the light beyond red, which is longer wavelength light, and Hubble does like the bluish and UV, which is on the other side of the spectrum.
And so, is it just that the optical part is just not necessary, or could you even add an optical element to JWST and have both the infrared and the optical? Or?
You couldn't add anything to it now, for sure.
Yeah.
But why infrared? Why not continue with the optical? And it's because it's because it was a part of this. It's a part of the science that we weren't getting with Hubble, right? So it was like we've already done this. Now let's do this, and you get different information out of it. So there's a couple of things. With the infrared light, we're able to look further back in time on galaxies. So we can look back to when the first galaxies were formed. With optical light, it's not as easy to do that, because the first galaxies were shining. The light that we get from them has been traveling through space for billions of years, and is now infrared light. So we need an infrared telescope if we want to see those first galaxies. But then also, a very clear usefulness of infrared light is when you look at dust. So dust, you might recognize dust's impact when you like look at. Have you ever been at a campfire and like shone a flashlight through the smoke?
Yeah.
Yeah, and you can see there's dust there, and your ash or something.
Or whatever,
yeah, and your flashlight is bouncing back at you. The optical light reflects off the dust.
Okay.
So you can't see through it as easily. Right. But infrared light goes right through it. So you can see through dust with infrared light. You can look into locations like where stars are forming, because stars form in these big clouds of dust that you can't see with an optical telescope. Or at least you can't see the inside with an optical telescope. So an infrared telescope is designed to do the things you can't do. And it's really, really useful, precious science that you want to have. Yeah.
And so you said, did you say 1.5 million kilometers?
Yeah.
So does that put it outside of Earth's orbit then?
Outside of the moon's orbit, even. Okay. The moon orbits at like 400,000 kilometers. Okay. So it's beyond that, yeah. So, okay.
I don't even know what that means.
Yeah, it's far. It's far.
Yeah.
And we put it that far out because we want to be away from. It's an infrared telescope. We don't want it to get. We want to be out in nice, dark, cold space.
Okay.
In infrared, you might be. What is infrared light? It's redder than red light. We tend to experience infrared light as heat. So when you feel heat, you're feeling infrared radiation hit your hand. So heat is a bad thing for a telescope that's trying to sense infrared light. So you want your instrument to be in a very cold place, away from any sources of radiation. Like you want it to be blocked from the sun, so it has this huge sun shield. I don't know if you've seen that. It's got this big sun shield it had to unfurl, and it's way out there in dark, deep space, so that it can be nice and cold and
so it's not orbiting,
sense the light from far
away. The Earth or any.
Technically, it's orbiting the sun.
Okay.
Yeah, so it's in an orbit. Now, there's the interesting thing. So this is a fun conversation. Is where did you actually put it? If you think about gravity, what you know about gravity, what we all know about gravity is that like if you hold a pencil above a desk, it's going to pull it to the ground, right? It's holding you in your chair, right? It holds the moon in orbit around us. That's what gravity is doing. And you can then you can imagine a scenario. So imagine you're like an astronaut and you're at Earth and you start flying towards the sun. You can imagine there's a place in between the Earth and the sun where when you get wherever that place is, you'll feel the same strength of gravity coming from the Earth as the sun. So it's almost like you'd be being pulled equally in two directions, right?
Yeah.
So that is called a Lagrange point.
Okay.
It's a location of stable gravity where it's sort of like a little sweet spot, and you can calculate exactly where that spot is with like Newton's laws of gravity. There are a few others. There's 4 others. That's one of them, right in between the Earth and the sun. But one of them is on the other, exactly opposite the sun, on the other side of the Earth. It's called the L2 Lagrange point.
Okay.
And that one seems less intuitive, and it just comes out of the math. But that's where JWST is. It's exactly opposite the sun, directly away from the sun, about 1.5 million kilometers in orbit around the sun. So as Earth goes around the sun, it stays in that spot constantly. Almost think about it like the Earth is always blocking the sun as much as possible.
Yeah. Okay, so it is still feeling the effects of Earth's gravitational pull in addition to the sun's gravitational pull.
Yep.
Okay.
Yep.
Okay, so it's always going to be in alignment with the Earth then, to some extent.
Yep. Oh yeah.
Unless I'm super simplifying that, but
yeah, no, you got it. It stays with the Earth, and they both go around the sun sort of at the same rate.
How the fuck do they do that?
Well, there's these 5. It's really cool the way the math works out. We call them Lagrange points after the mathematician that figured it out. The one that I told you makes a lot of intuitive sense. The one in between the sun and the Earth, right? Yeah. That makes a lot of intuitive sense. But there are 4 others that don't make as much intuitive sense, but they are still gravitationally sweet. And there's sort of stable spots that you could put things, and they kind of sit there without much effort.
Is it because of the other planets that also have an effect on that too, or
it's just the sun and the Earth? That's it. Okay. Yeah. Right. Yeah. One of them. Another one is ahead of us in our orbit. So if you follow Earth's orbit a little bit ahead, there's one there. There's one trailing us in our orbit, and then there's one on the other side of the sun. So there's these 5 Lagrange points, and L2, which is where JWST is a good spot to put that telescope.
This person, Lagrange, is that what I'm saying?
Yeah.
Yeah. Like, how do they even think to figure this out or look into this? Like, I don't even know how that happens.
I think you're looking at, I don't have a great story for that. But I remember learning it as an undergraduate student, where this was like one of our lectures was like deriving the Lagrange points, and it comes out of gravity. It comes out of understanding Newton's law of gravity and how two sources of gravity interact with each other. And you end up with these, if you do the calculus of it all, you end up with these spots. Yeah. It's wild.
I want to get into the learnings of JWST, but before I get into that though, just like as an astrophysicist, I guess, I don't know if this sounds stupid, but based on the laws of physics that we know, like, are those laws do you think they could be violated in other, like out there, or do you think it preserves throughout the universe?
Yeah, good question.
Is it a good question? I don't know.
No, it's a great question. The ultimate goal of astrophysics is to uncover the ultimate truths of the universe, right? And I would say, I'm not active. I don't feel like I'm actively contributing to that. But great scientists, both currently and before me, have done a really great job at uncovering some of those ultimate truths. There's things like the forces of nature, the fundamental forces. So like gravity being a fundamental force, electromagnetism and the strong and weak. These fundamental forces that shape the universe. Like that's pretty solid truth. One thing that, when you're asked this question, one thing that leaps out to me is our understanding of how gravity acts. And the way we understand it currently is through the theory of general relativity, which is Einstein contributed back in the early 1900s, which describes gravity as it acts, how it creates an attractive force, and how that attractive force can be calculated. And it's very successful. It's one of the most incredibly successful scientific accomplishments of humanity ever. It's been tested numerous times, and it passes. It always passes. But there's always a chance when you do some of these tests of these big theories that it may not perfectly predict. For example, trying to understand how galaxies collide with each other. That's a good test of general relativity and mapping where mass goes, and it survived those tests. Testing a really great one is testing how general relativity is really well tested in extreme situations. So like around black holes, near black holes, spinning black holes, and how light or matter acts near those. And just recently, in like 2015, 2016, 2017, they started testing the mergers of black hole theory.
Okay.
Where if you take two black holes and you merge them together, Einstein's theory predicts that some things will happen. And then they finally were able to measure those things happening. So I guess what I'm trying to say here is we're not done testing. We have these like some fundamental truths that we've gone into serious detail on, but we are still working on testing them to see if they are the actual final truth. And I think we all know that ultimately we're only able to do so good a job in all science is approximating nature, and we just want to make our approximations as close as possible. But if there's always one more pebble to turn over. There's always one more grain of sand to put on the pile. So it's not complete in any way.
Yeah. No, thanks for that.
I don't know if that answered that question, but
well, no.
I wouldn't say of what we know. I can't imagine that anything is going to be overly violated, like where we would throw it all out and be like, we're completely wrong. I don't think we're at that. I think we've done a really good job of narrowing down on what's going on in the universe, but there's a lot still to figure out.
Yeah, I mean, it's just amazing what like the short amount of time that science has kind of really been a thing. Like maybe 400, 500, 600 years, maybe, I don't know how long, but just the amount of discoveries we've been able to make in that short amount of time, which is like such a short, like in terms of the universe is like it's a drop in the bucket, obviously, right? But the discoveries we've been able to make, even just to identify like the Big Bang and that we know that there were some forces that brought that together, but I think if they're still discovering what those forces really are or how that even happened, but like just in that short amount of time we've been able to get to that point, it's just amazing.
I am equally blown away by humanity's progress over the last couple of hundred years, not just in science, but in like engineering and what we've built in the last century. Computers are like, those are new, right? Computers didn't exist in like the 60s and not really, and now they're like, it's like you compare a computer like today to a computer then, like it's mind-blowing. And this is one of the reasons I do science engagement so much is it may seem like someone pointing a telescope at a black hole and trying to just learn about it for the sake of learning about it. It may seem like a waste of time to some, but all of those scientists around the world doing all of those random questions are contributing in some way to some cool technology you have, or some advancement that humanity has made, or some structure of our society that we rely on. The research that scientists do are so fundamental to our innovation. Even if the individual accomplishments of a single scientist don't translate to that, the collective approach to science has done wonders.
Yeah, for sure. When you think of JWST and some of the recent discoveries, what are things that people don't really know about that really stand out for you?
Well, so my favorite thing about JWST is that it was designed with exoplanets in mind. So back when, this is cool. Here's a cool history of science for you. When Hubble was launched in, I think it was 1991,
okay,
exoplanets did not exist. Meaning, we hadn't discovered them yet. Lots of astronomers expected them to exist. And an exoplanet is a planet orbiting another star. We have 8 planets in our solar system. You go out and you look at stars at night. All of those stars have planets orbiting them. But we hadn't discovered them yet. Now, fast forward to when JWST launches, which is 2021, exoplanet science is now like a department at a university, right? You have, and in Canada specifically, there are some incredibly good exoplanet researchers, and their job is to find exoplanets around other stars, determine what kind of planet they are. Are they like Earth? Are they like Jupiter? You know, what are they like, right? And now, since we have this telescope that was designed in the exoplanet era, it has tools that can be used to study the exoplanets in detail. And one of the more recent ones, so it started collecting telescope data in June-ish, and over the last few months, they've released a couple of spectra of exoplanet atmospheres. So this is what they do. They point the telescope at a star that they know an exoplanet is there. It's already been discovered.
Right.
From our point of view on Earth and from JWST's point of view, the planet's going around and it passes in front of the star from the telescope's point of view, right? So the planet it's like a little mini eclipse, right, sort of.
Yeah,
the planet is passing in front of the star.
Yeah.
If that planet has an atmosphere, then the light from the star is just right around the edges of the little planet going around. The light from the star is going through the atmosphere. It's transmitting through. And when you put light through a gas, the gas always leaves a fingerprint. What it does is it absorbs little bits of light in specific places. Like if it has hydrogen in its atmosphere, the hydrogen will absorb a little bit of red light.
Right.
And if it has carbon dioxide in its atmosphere, it'll absorb a little bit of other kind of light. So this fingerprint is left behind as the light goes through the atmosphere. So they take the data from JWST and they can look at the spectrum, the rainbow of light, and see what kind of gases are in an atmosphere around a planet, around a star, 50 light years away, 100 light years away, 1,000 light years away. This is... And not only can they do it, it's built to do it for like thousands of exoplanets. So that's just cool on its own. But now think about, before we were able to do this, all we could really say about an exoplanet is like how big it is and how far away it is, maybe a little bit about its mass. But if you can study the atmosphere of a planet,
that has implications.
Then it has implications. Like imagine you studied our atmosphere and you found oxygen and you found methane, right? And nitrogen, like that, those are indications of life. If you find the same things around exoplanet atmospheres, like it's gonna change the game. It's gonna completely open up what we think a planet is in the universe.
And our detection of these atmospheres, like is it fairly accurate? Like
oh yeah, like the data that I've seen, there was one that they pointed out, I forget the name of the planet, and they were like, look, here's a clear indication of carbon dioxide. CO2 right there, boom. This is checked by hundreds of scientists. Like this is a legit detection of CO2 in an atmosphere. So it's accurate, it's based on all of understanding. It's good. I mean, you have to couple this with a lot of other things, right? So you can't just you can't just say, oh, CO2, that means life, right? You can't do that. You need a variety of things.
Sure.
To make a big claim, you need big evidence, right?
Yeah.
So, this is one part of looking for life in the universe. But yeah, it's accurate, and I'm really excited to do it. What they've done so far is big planets, like gas giant planets like Jupiter. I'm really excited to see the data come out about terrestrial planets, little tiny rocky planets. What do their atmospheres look like? Because that's way more close to home, right?
Sure. Wow. Very.
And looking on it, and just to add on to this, this is like Canada's bread and butter. So you go over to like McGill in Montreal, and there's like a whole team of exoplanet researchers there using JWST to do this work. And not just McGill, but like they have a good research group there. They're all across the country. Canada has a lot of exoplanet scientists. So Canada's right there doing this work.
Is JWST just constantly sending data back, or is there like what's the control on it look like? Like, can someone actually direct what JWST should be pointing at, or?
Yeah, wow, that's a good question. So there's a whole office group of people designed to manage JWST, and they do the telescope proposal situation. So they call it cycle 1, cycle 2, cycle 3. And you as a scientist, if I wanted to use JWST, I got to write a telescope proposal, submit it to them, and then they adjudicate it. They determine who deserves the time and who doesn't. And then there's a control room, like a mission control room, that points the telescope and collects the data and then sends the data back through NASA's Deep Space Network.
That's got to be the most competitive telescope proposal or process ever. Like, who
I would
actually
imagine
gets time, right? Like,
I would imagine, at the moment it's probably the most competitive telescope off the planet.
Yeah.
But it's incredibly competitive. Interesting fact, Canada has guaranteed time.
Oh.
So what that means, and the reason is because we contributed some hardware. So part of the instrument is built in Canada. So when Canadians apply, we're guaranteed 5% of the observing time. And so when the Canadians apply, for that 5%, they're only competing against other Canadians. So that it's still incredibly competitive, but you're not competing against the entire world.
But see, that's an interesting point or fact, because like the fact that Canada's contributed allows us access to it, right? I don't know if like people necessarily, like, I'm sure it was a lot of money, and maybe people think, oh, that money could be best used somewhere else. But like, if we didn't contribute to it, like, we'd be at the mercy, or we'd be competing with so many other folks. But we have this dedicated time. But then why don't we also in Canada have like a large optical telescope, like, we have like somewhere in Jasper or somewhere in the Rockies or something? Like, why doesn't that exist in Canada?
Well, so we have. So you say you're at the mercy of the rest of the world. Like the Hubble Space Telescope, we didn't contribute to. Canadians use it, but usually through partnerships with other groups.
Okay.
But Canada has a good history of astronomy. So there's a couple of really, really incredible optical telescopes on the ground. Let's see. There's one in Montmagantic, which is just outside of Montreal. Great observatory. York University has a 1-meter telescope, although it's in Toronto, which makes it a bit difficult to use for deep space science, but they do some really great research with it and outreach. So in Victoria, or just outside of Victoria, there's the Dominion Observatory, which is an optical telescope. It's been there for 100 years now, and it does some great work. And there's more, but Canada has contributed monetarily to the construction of big optical telescopes all around the world. For example, the Gemini telescope, the one that I used. We contributed money to that, and so we get guaranteed observing time. Another one is the Canada-France-Hawaii telescope, which is on the summit of Mauna Kea, and we also contributed to the building of that, and we have guaranteed observing timing on that. So we do have optical telescopes. They're not all in Canada, because Canada, especially for an optical observatory, Canada isn't always the best place to build one, because you're trying to avoid clouds and you're trying to avoid bad weather. You build them in places that have no clouds and no bad weather. So, and access to infrastructure is a problem as well. So we do have optical telescopes on the ground, but we've pooled our money into bigger telescopes elsewhere on the planet. Okay,
we just wouldn't get good bang for buck if we maybe had it here in Canada, like with the same size and scope and scale of those telescopes are in Arizona.
You might find some observing places in Canada that are as good as that, but I don't know of them. Though there's a group, the Canadian astronomers, like the professional astronomers of Canada, we're pushing for a Canadian-led optical telescope in space that would sort of be like a Hubble replacement, and it's called Castor. And that is currently we have. I'm not a part of it, but the scientists in Canada that are working on it have developed the idea and are working on pushing it forward for funding and building. So Canada wants to do stuff like that. Absolutely.
Yeah, cool. I'm already looking at this. Time has just flown by. It's already hour 10.
Oh yeah.
That's amazing. Are you okay for a little bit more time, or
yeah? Let's keep going. Sure.
Okay. I also want to talk about the Artemis moon mission that happened, and just like the purpose of that, and it's ended, right? Like it returned back, I think, right?
Yeah.
So tell us folks about why this even happened. Like why? First of all, I mean, I've always been curious and never really dug into it. Like why haven't we returned back to the moon? Right?
Oh man, and that's a good question.
That always like obviously feeds the conspiracy nuts. But I mean, but why haven't we taken the time to go back? Is it?
Well, so you start with I think the question to ask then is why did we go to the moon? So that was the reason that we went to the moon, and it wasn't it was NASA. Was because they had a national impetus to do so, right? They were fighting the Soviets, right? And they wanted to be the winner, and like they weren't hiding the fact that they were racing against the Soviets, right? This was like that was the goal.
Right.
We're gonna beat them to the moon.
Yeah.
And so they rallied around that goal, like. The amount of money that the states dumped into space research at the time dwarfs what they put into it now.
Okay.
But I don't mean that in a bad way, because the outcomes of that research, like computers can be traced directly to the Apollo program or the Mercury program. The materials research, like the materials that you see in like homes and apartment buildings and clothes and like eyeglasses and shoes, a lot of that came out of it. Like it was a boon for scientific and engineering and materials research. So there's this national impetus. They're in the Cold War. They land on the moon, but in a lot of ways, it's running before walking. The reason to get to the moon wasn't scientific. It was something else, and then. You can't sustain that level of funding. So the Americans, they win their race, and then the government's like, okay, like we can't do this anymore. We can't spend this much money on space. Although maybe I'm biased. Maybe they should still. But they peel it back and they start siphoning it to other things. But I think that's a good thing, because we didn't need to go to the moon then. What we should have been doing is what NASA did next. And that is building a presence in low Earth orbit, under 1,000 kilometers, under 2,000 kilometers, learning how to be in space close to home, where you can get back easily. You can get there relatively easily. What does this mean for the human body? What does this mean for long-term space flight? What materials should we be building spacecrafts out of? How do we run missions? How do we, all of those things we needed to start from scratch and build that all up. So the reason we haven't been back is because we've been learning how to be spacefaring. And that culminates with this International Space Station, which is the most complicated spaceship ever built. Those that don't know what the International Space Station is, it's an incredible piece of hardware. It's only about 500 kilometers up, 500 kilometers up. Orbits around the Earth once every 90 minutes, and it's the size of a football field.
Wow.
Like if you've ever been to like a in Edmonton, like if you ever go to a CFL game, right? Like that entire thing is the size of a space station.
Wow.
Right?
Yeah.
It's crazy how big it is, and it whips around the Earth at 30,000 kilometers an hour with 6 to 10 astronauts on board all the time. And they live there for months and months at a time, learning how to be in space. And we've done that for decades. And now finally, NASA and the rest of the world, we're ready to make that next step. We've learned how to, we've for the most part perfected low Earth orbit. The next step for humanity is perfecting lunar operations. And that's what the Artemis program is. Okay. So the Artemis generation is all of the missions and humans and people and engineering that's required to get humans to the moon. And Artemis 1 is the first mission in that whole program, which launched, it was like, I forget, it was like 30 days ago ish that it launched. So that's the whole backdrop. Yeah. So Artemis 1 is the first mission, and it's an unpersoned mission. There's no humans on board, but it's a full dress rehearsal. The whole thing, the human spacecraft rated for human spaceflight, the propulsion system, the communication system, the heat shield, all of the human operations on the ground that would speak to the spacecraft, everything. Send to the moon, orbit the moon, come back.
And that was the first time we've ever like orbited the moon, right?
Since with a human rated spacecraft, it's the first time that it's been done since the 70s. Okay. Though we do have a spacecraft orbiting the moon right now, and a scientific spacecraft, a robotic spacecraft that's taking images of the surface. Okay. But that's not human rated; it's just a robot. The Artemis mission had on board the Orion capsule, which is built for humans, and they were testing to see if a human could survive that mission that just happened. Yeah. And if the human could make it back to the Earth and go through the atmosphere, go through the fiery stuff and the parachutes deploy and all that. So it looks like everything went as good as or better than it could have. Cool. So that's good. Yeah. And what that means for us is that Artemis 2 is going to get a go-ahead sometime in the next 2 years. Yeah. And Artemis 2 is going to do the exact same thing, but with humans on board. Right. And the best part about it, there's going to be a Canadian on board.
That's awesome.
One of the 4 Canadian astronauts that we have, one of those 4 is going to be flying to the moon on that mission whenever it launches, 2024 probably.
And is the hope that they would actually land on the moon and then
no landing? This is what they did in the Apollo era as well. The first human missions were orbits around the moon. Oh, okay. And then once they do those rehearsals and they've perfected that with humans on board, then they'll start doing the missions down to the ground. Okay. I doubt a Canadian will be a part of that, though I could be proven wrong. I have no inside information on that. Yeah. But there's definitely going to be a Canadian orbiting the moon, which is huge, right? Like that's a big deal.
So it kind of sounds like then, as far as with the Apollo missions and getting to the moon, and this time getting around to the moon, like it didn't seem like the propulsion technology was an issue. Like it seemed like, from what I'm hearing, it was more of a priority piece. The funding was not sustainable, which is why we didn't go to the moon. But if we wanted to, we probably could have. Is that fair to say?
I think the technology still existed, and we knew how to do it, but it wasn't a sustainable practice. So yeah, you need a fully oriented space program to sustain something like that. And that's why I say it's like sort of running before walking. We did it, we made it happen, but we didn't do it the most efficient way, and we didn't do it with a whole picture of what space exploration should be and why we should actually be going to the moon. So like, if you're doing that, you're not doing it for the right reasons. You're doing it to win the race. So it's good that we stepped back from it. It's good that NASA deprioritized it, because we really needed to learn how to do the low Earth orbit stuff. We needed to build a space station, and even more importantly, we needed to work as a unified world, right? The space station isn't just a NASA project. It's Russia, Canada, it's got Japan, Europe, and like 15 other countries involved in it. So we needed to sort of unify there a little bit. And now that we've sorted that out, it's now time to do the next big step.
But what's still confusing me, though, is that if Artemis 1 was about design the spacecraft that would be used by humans to make sure that everything is essentially kosher for it to come back safely, all that kind of stuff, Artemis 2 is now going to bring humans into that same situation. And then hopefully then we could then go back to the moon, land on it, and go from there. But we did that, right? So then, like, what would we still need to, I don't know, this may sound stupid, but what would we still need to learn then? Like, if we've already been to the moon and we know what it takes and the impacts it has on humans or whatever, or maybe we just didn't know enough and it was such a rushed mission. I don't know, but
yeah, I mean,
why that phased approach? I guess
there's so much more science to do at the moon. One of the major differences between the Apollo program and the Artemis program is the location of the moon, where you're going to be landing humans eventually. Apollo landed them all on a variety of places. There was a bunch of missions that landed, but they were sort of on the Earth-facing side, mostly in the Maria, in those dark areas. But the Artemis missions are targeting the South Pole, because the South Pole has a couple of craters there that never, the bottoms of the craters right on the South Pole never see the light of day ever. They're permanently, we call them permanently shadowed regions. And in those regions, we find there's water ice, large amounts of ice, water, like H2O frozen. And that, if you want to, then what you're doing is you can picture yourself, what can I use this water for? Well, obviously we can use it for drinking, but if you break apart the H and the O, you can get different fuels, you can get breathing air. And now you're learning how to live off the land, right? Because if you want a sustained human presence throughout the solar system, learning how to live off the land is really important. What do we have there and how do we use it? So going to the moon, going to the South Polar region with the permanently shadowed region, we're going to learn how to harvest water and use that water to maintain a human presence. And that's only a 3-day trip. And then you can use what you learned there to go and do the same thing on Mars. And that's a 6-month trip or an 8-month trip. So you don't want to just jump to an 8-month trip, right? You want to learn how to live on the moon safely, out of reach of humans, but sort of closer, 3 days drive is okay. And then when you go to Mars, which is the next big step after that, you're ready for it.
So the moon is the next step. Like if you think about the International Space Station, low Earth orbit, we get to the moon, then the ultimate goal there is Mars and obviously beyond.
And then what's the question? There's my question is what's beyond on
what's
Mars?
Next?
I think that the next step for human space exploration would be going to an icy moon, which would be Enceladus or Europa. So Europa around Jupiter, Enceladus around Saturn. I don't know where else. Yeah, those would be my two biggest ones. There's a few. Ganymede would be an interesting one. Callisto's an interesting one. Titan is an interesting moon. Yeah. So all of those places would be, but that's like 150 years in the future.
But those launches probably would have to happen off of Mars, you think?
And you nail it on the head. One of the other things that you do with this is launching spacecrafts off of the moon or Mars is easier because their gravity is smaller and their atmospheres are either non-existent or thin. And that makes it easier to get into space. So if you can imagine a scenario where you can not only live on Mars, but you can do some of the building of rockets on Mars, then that makes it easier to fly through the solar system.
Yeah. So the next question, space propulsion. I wanted to maybe end off on this, and then I'll ask my final two questions. But just in terms of propulsion technologies, like I think Elon Musk was on Joe Rogan's podcast. Joe Rogan asked him, he's like, is there any kind of technology that doesn't require sort of this kind of combustion sort of propulsion system? And he's like, I can't think of anything, right? I mean, obviously it's just one person's opinion. He's not I wouldn't imagine he's the subject matter expert on this entirely, but at the same time, I mean, when he says something like that, it carries at least, mainstream popular weight, right? But then I hear the technologies like warp drive and all these kind of things. So like what excites you about space propulsion, and what do you think those technologies look like?
So Elon Musk isn't far off from this. It depends on what you're trying to do. If you're trying to put something really small into space, like a little satellite that's like this big, like a CubeSat or a nanosat, maybe you don't need a combustion reaction. There's a startup company, and I forget the name of this startup company, but what they do is they've been testing this method of getting things into space by literally throwing it. What they do is they have this crazy spinning centrifuge thing. They attach the payload onto the end of like a wire or something, and they spin it up like crazy, and then they let it go and it shoots up. And they can actually achieve some pretty high altitudes with it. And so they're investigating this. There is also the idea of, and for those listening, I don't know if this is possible. There's the idea of space elevators, which has been the subject of science fiction for a long time, which is a literal elevator into space, which is technically possible, though engineeringly difficult is an easy way to say that. But all of that stuff is like the spinning one that I was talking about, like that's going to launch a little tiny thing. If you want to put like a human and all of their living quarters in a habitat and you want to get that off the ground, like the delta V, this is what you need to, the space engineers are always thinking about delta V. I'm starting at 0 kilometers per second on the surface of the Earth. I need to get like 8, 9, 10, 11 kilometers per second to get into orbit around the Earth. So to go from 0 to 11,000 meters per second, like, or 11 kilometers per second, like that's a lot of energy. And at the moment, the only thing I can think of to get a human off the ground is some kind of combustion reaction. Yeah. But then
once you're outside of, then what happens?
Once you're outside of the well of Earth's gravity, once you've gotten beyond the atmosphere and you're not so held on, there are some really interesting options. One that we've tested over the last 15 years is ion propulsion. There's been at least one really successful ion propulsion demonstration with a spacecraft called Dawn. It was launched with a chemical rocket off the ground, like a regular rocket. Once it was in space, it used an ion engine to fly off to a asteroid called Vesta, and then off to the dwarf planet Ceres after that, using the ion engine. And an ion engine works just like any other rocket. It shoots stuff out the back, but instead of doing a chemical combustion reaction, it's just doing this. What it does is it strips atoms from its electrons from the atoms, and then shoots the electrons and the atoms out the back. And it's the same idea. You shoot something backwards and you go forwards, but it's using little atoms and electrons to do it. And it's a very, very small thrust, but if you do it for you can turn that engine on and run that engine for like a week or 2 weeks or a year, and it'll slowly build up acceleration. And you could conceivably use engines like that to move humans around the solar system. Say you wanted to go from the moon.
And those would be electric-based engines then? Like you could power it through solar or something like that?
Oh, yeah, good question. I guess you would. Yeah, you would be, the electricity on board would be powered. You know what? I don't know the answer to that question. It depends, because I would imagine you'd want to have a scenario designed for when you're too far from the sun. So you'd use some sort of nuclear reaction, like a nuclear decay, like plutonium or something.
Yeah. Yeah.
But yeah, I imagine Dawn had solar panels on it, so I imagine that's what it was used for. One of the things, at least. So that would be a way. And then there's also, and it sounds crazy, but solar sails. So this has actually been technically demonstrated in space. The Planetary Society launched and so did the Japanese, launched a sail. It was compact, and then it unfurled, and I think it was about the size of a tennis court. And they oriented it so that it would catch solar wind and catch solar radiation and use that to accelerate. And they demonstrated that they could do it. And it's like literally like sailboats on an ocean using the wind to move around. It uses solar radiation to move around. And that also can generate quite a lot of acceleration if you leave it for a long period of time. So these are methods that could be used viably in the future for moving large amounts of mass around the solar system. They still need testing, especially for human use. But yeah, it's an interesting future that we have.
So you likely need the combustion-based engine to get us off of Earth, but then once you're kind of outside of Earth's pull and all the things that Earth has to offer, then you can maybe use something else. Yeah,
definitely. There's definitely options. Like, you could never use an ion engine to get off the ground. It just doesn't create enough thrust. You need that combustion punch to get off the ground. Yeah.
Okay. All right. Mindful of the time, and I appreciate the conversation. And we always I want to talk about space junk, but that we can leave that for maybe in a future
discussion part 2.
But
yeah,
yes, for sure, because there's so much to talk about. But we always ask our guests a couple of questions. Are you okay if we move on to those?
Yeah, let's do it.
Okay, so we have our 5 for dinner question, which is dead or alive, who are 5 people you'd want to have supper with? And I guess that bit of twist is like, would you want them individually or together?
Definitely together.
Okay.
Because then you're seeing... Okay, so I was thinking about this. So it's funny you mentioned Elon Musk, because I really think it would be fun to chat. I wanted to chat with Elon Musk for a long time. Not because I revere...
Even though he owns Twitter now, like you're still okay with him now?
I don't know, man. That whole Twitter debacle.
Yeah.
He is... He certainly, don't get me wrong, the contributions he's made to society are great, right? Obviously, right?
Yeah.
But he definitely hasn't... He's... Like, the way he's treating space doesn't jive well with me. And certainly the way what he's done with Twitter is weird. So one of the things he's doing with Twitter, or with space, is launching all these satellites. And that would have been a great discussion topic on space debris. But the amount of satellites that he's launching into space is dwarfing all of the satellites that we've ever launched into space in all of humanity and history ever. And that's a defining moment in human history. We are exponentially launching things into space, primarily due to him. And it has had large impact on astronomical sciences. Now, to SpaceX's credit, they are now dialoguing with the scientific community. But I would still love to just sit with him one-on-one and, like, off the record, like, pick his brain on the impact he thinks he's having on science. And try and communicate to him the impact he's having on science. So Elon Musk would be a really interesting one to chat with.
Because once those satellites are out there, Jesse, like, they're out there, right? Like, you can't do anything. You can't bring it. Like, we can't clean up this debris.
Well, it depends. We can. It depends on where they go. The low Earth orbit ones, like anything under 2,000 kilometers, eventually will... Well, some of them will eventually come down. Like, especially at the 500, 600, 700 kilometer mark, the atmosphere is still a little bit there, and it drags them down. But yeah, anything beyond that, there's nothing to drag them, and so they're just there. Like, they're there until someone wants to go and get them, and it would cost millions to send a spacecraft to go and get them, and nobody's ever going to do that.
Right.
So the name of the game for that is creating policies that requires people who launch things into space to deorbit them at some point. But that's a whole other thing. On the 5 for dinner. So Elon Musk, I think Galileo would be incredible. That guy, from what we know through history, was a very smart guy. He was the first person to discover moons. Like, nobody knew moons existed. Like,
right.
We had nobody at his time. They were still figuring out if the sun was at the center or the earth was at the center.
Right.
Yeah, and so nobody really realized that our moon was a moon. Not really. And so he discovered moons around Jupiter, which is like, like, he discovered a new category of thing. That's cool.
Yeah.
Oh gosh. I think I don't know. 5 for dinner. Stephen Hawking would be a really interesting person to talk to. I would love to speak to, like, sit down and talk with an astronaut. Like, maybe Chris Hadfield would be a really fun person to talk to.
I'm surprised, like, you haven't met him, or you haven't.
No, I've never met him. No.
Yeah.
There's some really great scientists throughout history. Like, oh man, there's so many. I don't know. There's so many cool people that'd be interested in talking to. Marie Curie. Oh my gosh, Marie Curie.
Oh, she's actually on my list.
No kidding. Oh yeah.
Yeah. She's on my 5. Yeah.
Like, not only did she discover, like, elements, but, like, she created methodology. Like, she created nuclear science in a way. Like, that whole field of, like, figuring out what radiation was.
Yeah.
Like, she, like, that's a huge contribution to science, and she would be a really interesting person to talk to. And I'd be interested in asking questions related to how she, like, the impact she was making, and if she felt she was making that impact.
Right.
And then also, like, the sickness that her and her husband got from it. did they obviously they must have known, but they did it anyway, right?
Mm-hmm.
And nobody knew that radiation poisoning existed, but they were smart people. She was smart. I'm sure they were, they're like thinking, at dinner that night, like, do you think it's the science we're doing that's like making us feel this bad?
Yeah.
They must have been thinking about it, and they still did it anyway. She was like, that's a really cool thing. Like doing science that's hurting you, but doing it because you're so interested in it.
Totally. And then the societal challenges too. Like, I mean, just her being, just being a woman in that field, right? At that time, like the challenges she would have had to overcome and the stigmas and all this kind of stuff.
Those,
it's incredible.
And trailblazers like her, make change happen.
Yeah.
But like the stigmas and the issues are still around, right? Like we still have those stigma and issues to a certain extent. So, I'd be interested to hear how Marie Curie would compare and see how far things have changed based on her push and what she's done.
For sure.
Yeah.
For sure. Okay, so you got Elon Musk, you got Galileo, you got Stephen Hawking, you had Marie Curie, and then you had
fifth. Oh, Chris Hadfield. Yeah.
Chris Hadfield. Yeah.
Man, can you imagine them talking to each other? That'd be cool. I just want to watch them discuss.
Yeah,
it's wild.
For sure.
Yeah,
that's an awesome
that is a really hard question. There are too many cool people to talk to. That'd be an interesting one.
It's really interesting to see everyone's answers, because what I've noticed is it kind of it does seem like it speaks to the person that I'm talking to. Like it's a reflection of who that person is. And I mean, with these 5, I can see how they're linked to you, right? But,
Stephen Hawking, like Stephen Hawking is his genius. It's unbelievable how smart that guy was. What he was able to contribute, I don't know how he could have, like, I've attempted to learn his science, and it's like, it's a whole nother level. Like his brain worked differently than everybody else's brain. It's genius.
Incredible. Last question, besides the circle of life, what do you know for sure?
Yeah. What do I know for sure? I don't know much. One of the things that I was a hard lesson to learn is that I'll never know enough. Right. So what do I know for sure? Almost nothing. Especially having a kid. Now I know even less. But I think that a good answer that I have to this is like sort of surrounds my career, is that I know in my heart that humans are curious. I know it, right? And you can't stop it. You can have discussions about, you can say, oh, we should be putting money towards this, or we should be putting tax dollars towards that. And that's a great conversation to have, but you're never going to stop people from wanting to be curious and discover things. And we're always going to be spending money on it. You can't stop it. We want to climb the mountains. We want to go to the bottom of the ocean. We want to just figure out how a tree works. We want to figure out what frogs do, and we want to figure out what planets do. Like, we want to do it. And it's not anything other than it's just built in. It's like the thirst for more information.
Yeah. I
know that for sure. Yeah.
I love that answer. I don't think I've had that answer. I've had people say like they don't know nothing, and usually it's the academics that I'm talking to. I've had a few say that, which makes complete sense. But the thirst, the fact that curiosity is within us, and that thirst, you can't stop that. It's a really neat answer. Jesse, this is a pleasure talking to you. I really enjoy getting to know you, and getting to know you as a fairly new dad, and the challenges that you're going through, to just like your curiosity that you're showing, and just the fact that you are, committed to this outreach and educating people. I think that's fantastic. So thanks for making time today. And hopefully I get to talk to you again in the future. Maybe if you're interested, we can do another episode at some point. So there's always so much to learn. But thank you for making time for me today.
Yeah, you're very welcome. This was a really fun conversation, Rupesh. I don't often get a chance to like do detailed conversations. So this is a chance. It was a really fun opportunity to sort of like go through all of the little nooks and crannies of stories. And but there's still more, right? So I'd be happy to come back and do some of the content we didn't get to.
That's awesome. We'll put all of Jesse's info in our show notes, and you'll get a link to his bio, and check his page out. And thanks again, Jesse, and hope to talk to you again in the future.
Yeah, have a good one.
All right. Thanks, everyone. Bye-bye.